So for this first exercise, we want to write the minimal sum of products form for this Carnot map in exercise 1 here. And what I have here at the beginning is not the minimal sum of products form, but this would be the canonical sum of products form. This would be the set of the set of each individual term that represents each of these ones in the map. And again, the ones in the map really correspond to the ones that would be in the function column of a truth table or a truth function. These are the parts of the function, or the places where the output of the function should be 1. So if we're translating from a truth function, that's where these would come from. And any places that are blank would correspond to zeros, but we tend to just not write those because they aren't what we're considering. We're supposed to be focusing on the ones. So anyway, each of these terms corresponds to one of these ones. And so, for instance, this first term would be this one right here, which is in the first column, which would be x1 and x2, and then in the second row, which would be x3 naught or x3 prime. So that's the 3 factors that we have, x1, x2, and x3 naught. And so you can follow through each of these 5 ones, and we have all the different terms here. But the point of using a Carnot map is to try to reduce the expression down from this to its minimal form, to basically the fewest number of terms and factors that we can. And the real correspondence to this would be if we're designing a circuit and each of these variables is an input to that part of the circuit, and we have some output which is defined by this whole expression. Every factor here represents, well, I guess I should say, every multiplication between 2 factors represents an AND gate, because multiplication in our Boolean algebra represents AND, the AND operation. And every addition, so every extra term, represents an OR gate. So if we have a lot of factors, a lot of multiplications, and a lot of additions, and then on top of that, I should also mention the complements here, the negations here, also add an extra gate. That would be an inverter that we would have to put into the circuit. So every one of those bits of the expression adds complexity to the circuit. It adds extra parts. So in order to build a circuit efficiently, use the fewest number of parts that we can, we want to find the minimal sum of products form. The least number of terms and factors that we can possibly use and still represent the same function. Okay, so now to turn this into the minimal sum of products form, in our Carnot map, we want to find, the instructions get a little involved and complex if you go through the steps that are above here. But really the point is to try to capture groups of these adjacent ones into as few groups as possible. And I guess we could say as few groups and also as large of groups as possible. So let's get rid of this and take an attempt at this first. One attempt we could take here, let me start to circle some of these. Let's say we try to do something like this. So we're going to group these 2 ones together. We're going to group these 2 ones together. And then we're going to just leave this one out by itself. And have that just as its own individual group. So now, based on those groups, we can write the expression that comes from that. So we'll go one group at a time. This first group here eliminates the variable x2. And the reason it eliminates the variable x2 is that when we look at the 2 columns that this group spans, one of those columns has just x2 by itself. The other one has x2 prime, or inverted x2, or negation of x2, which means that the function can be 1 in this situation, whether x2 is 1 or x2 is 0, which would be the difference between these 2 things. And what that tells us sort of practically is it doesn't actually matter what x2 is, because no matter what it is, regardless of which of these 2 columns it falls into, it won't affect the result, because the result should be 1. So all we need here, notice that x1 and x1, those are the same here. We don't have the negation of x1 here, so we can't eliminate x1. We're going to have to include that. And then the same with x3. We have the negation of x3 in both of these both of these cells, both of these squares. But we don't have x3 included in here, so that doesn't get eliminated either. So we have x3, the negation of x3. And again, x2 is gone because we have both forms of x2 represented here, which kind of cancel each other out. So the next term, let's go to this group of 2 here. We'll look at what changes between the 2 elements in that group. And again, it's x2, because we have not x2 and then we have just regular x2. Whereas we have not x1 and not x1, nothing changes between those 2 squares, so x1, or the inverted x1, has to stay there. We can skip x2, but then this row has x3, so we'll have to include x3. So we're kind of looking at, with both of these squares together, whether each variable is represented by those squares or not. And if there's a change between the 2 different forms of a variable, we can just eliminate it. So then finally, we have this single group out by itself, which isn't grouped with anything, so we're not going to be able to use this trick where we eliminate something. We can never eliminate anything with a single a group of 1 element, because there's nothing to change between the 2, between more than 1 square. So for this square, we just have to look at what's in its column, x1 naught and x2, x1 naught and x2, and then in that same row is x3 naught. Okay, so this is a potential solution, a potential minimum sum of products form. But let's try something else to see if we can get it better. So let me actually change this to blue. We'll just hold on to that. And then let's redo this. Let's find some different groups. And I'm going to do something very similar, and I think this is the solution I have on the answer sheet. We'll pick these groups. We'll make that group again. We'll also make this group again, but instead of just leaving this element by itself, we're allowed to overlap these groups. So let's actually put this in the same group, or actually, rather, use this element in both of those groups, and we'll do something like this. Might seem like that's not a great solution because we're almost being redundant about something, but let's see how this turns out. So the first group should be the exact same as it was. Is this the same 2 elements? Okay, we get to eliminate x2 in this lower left group here. This top right group is also the same as it was before, so that'll be the same x1 naught and x3, but we're eliminating x2. And then finally we have this vertical group, which is going to be, well, we'll see what changes here. Going top to bottom, x3 is changing from its regular form to its inverted form, so that's going to get canceled out because we want the function to be 1 regardless of what x3 is. So all we have to look at is the column here, which is x1 naught and x2. x1 naught and x2, and we've eliminated x3. So this would be the expression that comes from this particular grouping of this Carnot map. And then finally, if we compare these 2 things, well, they both only have 3 terms, but this one has an extra variable in it. It has an extra multiplication, which would correspond to an extra AND gate. It has, even just 1 extra bit of complexity makes it less efficient than this new form that we've come up with. So this is going to be the most efficient, the most minimal sum of products form that we can find, and this is what we're going to want to use as our answer. So again, this is just kind of a game of grouping things. A lot of times the groups are obvious. We can group these 2 together, but then when we have something like this, I think most of the time we'd want to consider overlapping multiple groups rather than just having an element completely isolated, unless we have a situation where a square with a 1 is not adjacent to anything, and then there's no choice but to just have it by itself. The only way we can form these groups is if the 1s are either adjacent right on top of each other or just left or right of each other. And then I guess one last thing to mention about this one is we could make larger groups of 4 or 8 elements, but there's no way to do that in this particular exercise. There's no way to span 4 1s in the same row or in the same column or even in a square. Remember that when we do this, we can wrap around to the other side, but that's not going to help us form any larger groups. So this should be our minimal sum of products form for that problem.